Good morning, everyone. Let's get started with the first item on our to-do list. Astronomy and astrology are distinct terms, but they're often mistaken for one another. We're going to fix that here and now. It's important that taking a class on this, one of these topics, that you distinguish. So let's start with number one. We'll go through these one at a time. Which is the topic of this class? Prepare your cards. I gave you a hint saying it was one of these, so not both or neither. 3, 2, 1, vote. The correct answer is astronomy. Astronomy is physics and math applied to things in space. Astrology is horoscopes and stuff. Number 2, which is a field of science. 3, 2, 1, vote. Okay, I'm getting a variety of answers. The correct answer, which about 40 or 50% of you have, is A, astronomy only, period. Astrology is a pseudoscience, meaning fake science. It might superficially have some resemblance to science, and it might even look technical, which might make you think science, but it is incompatible with the scientific method. We'll talk more about that when we discuss the word falsifiable. There are no college classes in astrology. There are no legitimate higher education degrees that you can earn in astrology, but there are in astronomy. By the way, I want to make sure everyone's able to participate and vote. If you forgot your voting card today and every day for the rest of the semester, I brought my big stack of spares. So please raise your hand, and I'm going to ask one of our LAs to bring you one. Some spares there. Allison, let me give you some, just in case you see any hands. And I'll ask you guys to look with me the next few questions where I'm asking folks to vote. And if you see that anyone doesn't have a card but didn't want to stick their hand up, just go give them one. Number 3. Which has to do with stars and constellations. 3, 2, 1, vote. Okay, more than half getting this one correct. Both is the correct answer, which makes predictions. Three, 2, 1, vote. We're kind of split between B and C. A few A's. The correct answer is both. Different kinds of predictions, to be sure. To go back to 3 and 4 together now, again, we said that astronomy applies science and math and physics to stuff out in space. Astrology makes predictions about or connections between the relative alignment of celestial bodies and human events. So astrology makes predictions about human stuff and tries to draw a link between that and what the celestial bodies are doing. Astronomy makes predictions about physical things going on with the bodies themselves in space and doesn't try to link them to human events. Number 4, we did. Number 5. Sorry, before we vote on number 5, I'll say a couple more things about the predictions. Both astronomy and astrology make predictions that might turn out to be true and might turn out to be false. But pseudoscience predictions, like astrology predictions, are not falsifiable. Science predictions are falsifiable. Falsifiable is actually a good thing. Falsifiable doesn't mean false. Falsifiable means able to be proved false. And that's a good thing, because if something is false, you want to be able to demonstrate that it's false and know that. If something is unfalsifiable, then if it turns out to be false, you'll never know that. That's a bad thing. So falsifiable is good. And astronomy predictions are falsifiable, and astrology predictions are not. Science rigorously tests its predictions against evidence. Astrology does not. Okay, now on to number 5. Given that background about falsifiable versus unfalsifiable, which is fraud. 3, 2, 1, vote. The correct answer here is astrology, B, only. I was a little alarmed to see a couple of A's in there. No, the academic field of study of astronomy is not fraud, it is science. And science, as a larger endeavor, is not fraud because it is self-correcting. The scientific method built in allows untrue things or erroneous explanations to be found and corrected. That's the whole point. It's not the case that science never makes mistakes. Scientists never make mistakes, or science never makes mistakes. Mistakes happen, but they're corrected, they're found. That's what the scientific method is for. Always testing, mercilessly testing your explanations to ferret out those mistakes. But astrology, since it deliberately, like other pseudosciences, avoids rigorously testing its predictions, is not science and could be argued to be fraud. You might be picking up already that I kind of look down on astrology and respect astronomy. That's not to say that everyone who is engaged in astrology is a bad person. I just don't want it to be confused with astronomy. That's why we're distinguishing between them today. Number 6. Tests consistent with random. When the predictions are put to the test. Let's vote. 3, 2, 1, vote. The correct answer is astrology. On the rare occasion that someone, not an astrologer, but someone usually trying to test from the outside, because astrologers don't want to test their predictions against reality. They just like to make them and sometimes collect money in the process. But when somebody puts astrological predictions to the test and eliminates confirmation bias by actually recording how many turned out to be true and how many turned out to be false, and not just remembering the true ones because those are more memorable, that's what confirmation bias is. Astrological predictions are consistent with random every time. It's like rolling dice. You'll get the right number or the number you predicted sometimes, but only by random chance. So I'll say that astrology, as with other pseudosciences, are chicanery or charlatanism at worst, if someone is trying to get your money or influence your opinions or actions. And at best, astrology is woeful ignorance or harmless entertainment. Sure, go read your horoscope for fun if you want to, that's fine. But don't give anyone money for it, and don't let it influence your personal decisions any more than you would let rolling dice influence your decisions. Don't ever, ever give anyone money for anything related to astrology. Don't be a sucker. A lot of people confuse these terms. Maybe some of you in this room have misused one of these terms for the other in the past. Blanket pardon on everyone. No hard feelings. We'll move on. But from this moment forward, don't ever, ever confuse these terms again. Please. You're in an astronomy class, not an astrology class. And if you hear other people misusing the terms and you're inspired, feel free to politely correct them if you want. Don't be rude and condescending about it. But, oh, by the way, they're actually different. Astronomy is the science one. Astronomers, perhaps like other practitioners in fields with names similar to other things, get annoyed when people mislabel their life's passion. Perhaps like meteorologists and meteorologists often get mistaken for one another, like, oh, okay, it's just a little bit annoying. But, or I made another example here, or pediatrics versus podiatry. Different, but yeah, it's an honest mistake, right? With astronomy and astrology, it's more than annoying. It's like confusing nephrology and phrenology, because nephrology, the study of the kidneys, is a legitimate academic and scientific pursuit, whereas phrenology, the study of the bumps on the skull and trying to relate them to personality characteristics, is pseudoscience, and that's embarrassing. So that's why, word to the wise, try not to confuse these terms if you're ever posting online on social media or talking to an academic. Okay, speaking of often confused terminology, next on our to-do list is rotate and revolve, both completely legitimate words that belong in an astronomy class. I will demonstrate one of these with my body. Which one am I doing? Go ahead and hold up your cards if you feel strongly that you know. If you're not sure, you can hold up the rainbow. Oh, now I'm getting dizzy. I got to go back the other way. Okay. I'm seeing more greens than pinks in my little snapshots of this. And which one is green again? B, rotate. Yes, I was rotating. To rotate is to spin around an axis of rotation, an axis of spin that is through the center of the object itself. So I'm just spinning in place. That's what rotation is. So a synonym for rotate would be spin. Let's have you, now that you know the definition of rotate, demonstrate revolve. Seated where you are with, say, your hand. Maybe close it into a fist and make it revolve. What's that look like? You can use both hands if you want. Okay. Now I'm seeing, see, I didn't have you do this with rotate because you can't. Your wrist bones won't turn more than like 180 degrees or so. But with revolve, you can. I saw people doing something like this or something like this. To revolve is also to move in a circular fashion, but to move around an axis that is external to the object itself. And so going like this, the axis around which it's moving is here in the middle. If I were to demonstrate revolve with my body, the most natural thing to do is to revolve around another object that marks where the center is. So I would be revolving around this chair, say. What's a synonym for revolve? Go ahead and say it out loud if you know one. Orbit. Revolve is orbit, rotate is spin. Now, look at the cards in use again. Think about it for a moment. Three, two, one, vote. Good. The correct answer is, and instead of saying the letter, since it's just a one-word answer, go ahead and say the word of the answer. Both. Yeah. Hopefully, a lot of you knew this from earlier classes in science. How long does it take Earth to revolve once? Go ahead and say it out loud if you know it. A year, 365 days, 365.25 days if you want to account for leap years. And what object does Earth revolve around? The sun. And technically, they're revolving around their common center of mass, which is very close to the center of the sun. So the sun is wobbling a little bit as Earth goes around. That'll be important halfway through this semester when we talk about discovering exoplanets, planets around other stars, and how we can tell that they're there by their stars wobbling, even when we can't see the planet itself. But it's approximately true and fine to say that Earth revolves around the sun and to assume that the sun is stationary. How long does it take for Earth to rotate once? Go ahead and say it out loud. A day. It gives us the definition of a day. Earth spins on its axis, and so if you guys are the sun, Earth spins around, and the sun seems to set and then rise in the sky due to Earth's spin. So Earth's rotation on its own axis gives us a definition of a day. Earth's revolution around the sun gives us a definition of year. All right, piece of cake. Let's ask a less obvious one, I hope. Prepare your cards. Three, two, one, vote. Ah, okay, good. It wasn't so obvious. Yes, the correct answer, it turns out, is both. Who knew, right? C and C. We can't notice the sun's motion very easily. I'll show you a video clip probably next time or when we talk about the sun, when we track sunspots, which are dark blotches on the sun's surface. We can actually notice day after day they seem to go across the surface of the sun like that, and they kind of go at the same speed. That indicates that the sun is rotating on its axis. We can't see it with our eyes, but with telescopes and appropriate filters, we can. The revolution of the sun is even harder to detect. It's going around within our galaxy, orbiting around the common center of mass of all the other stars that make up our galaxy. And that motion takes a couple 100 million years. So that's really hard to notice from day to day or from year to year. Whereas the rotation of the sun only takes about 33 days, and so that's readily easy to track. Okay, got rotate and revolve, got falsifiable, which is a good thing. I wanted to remind everyone that there are office hours every week, and starting next week, a weekly homework party. I call it a party to make it sound more appealing, so you'll go, and your LAs are going to be there. So that is intrinsically appealing. I will endeavor to put the homework party on the, oh look, we can X out things that have already happened here. I hope you use this upcoming to-do list. Lecture today, yep, we're already here. Okay, so I have office hours Mondays. I won't put those on the to-do list every week, but they are on the syllabus. The LA homework party also on the syllabus. I know that Monday is a holiday and there are no classes, and the TAs will not be having office hours, but I will still hold my office hours because I know your first homework assignment is due on Tuesday night, and I want you to be able to ask me questions. So I'll still be there in my office unofficially to help you. I haven't checked with the LAs yet whether they're going to be available. I will, and I will update this after I ask them in private after class if they are able to attend their homework party on Monday too. Yeah, the LAs are your superpower to succeed in this class. They're not astro majors. I forget. What's your major, Allison?
International politics and French.
International politics and French?
Marketing.
Marketing. They took this class last year, and they unlocked the secrets of success in this class. Let them share those with you, whatever your major is. Yeah, let's get on to some math review and practice. That'll be the topic of the homework assignment coming up. It's due Tuesday night, as from now on our weekly homework assignments will be. The LA homework party and my office hours are on Monday to allow you to get your questions answered, and not at the last minute, but with a day's notice. The syllabus will summarize some of the math skills just in general. It'll say stuff like scientific notation and multiplying powers of 10 and knowing the terms million and billion and how to put those by writing out all the zeros or into scientific notation. We're going to practice some of those, most of those, in class today. It's going to at least illustrate these basic math skills that will come up again and again. The amount of math we're going to do today is not representative of how much math we'll do all semester. I'm front loading it to just give you the whole snapshot, and then we'll use the tools as needed. Homework 1, we'll let you practice. We use big numbers in astronomy. That's why scientific notation is convenient. And also, we like to be able to say the numbers in words when we have words for them. We don't generally say the words quadrillion and quintillion and sextillion and so on, but the ones that come before that, we do. So, don't answer this out loud yet, but write out in your notes right now how you would say that number in words. I want you to commit to it. Commit to your best guess. Not the scientific notation words, but the words. It'll have something with an illion in it as a hint. Okay? Now I'm going to count to 3 and ask you not to use the cards, but just to say the number that you wrote down out loud. 1, 2, 3, go. Okay, I heard a variety of illions there. Talk to your neighbor. Compare what you wrote with what they wrote. Try to come to consensus in 15 seconds. Go. All right. Let's try it again. 1, 2, 3, go. Okay, a vast array of number of syllables in that answer there. Here's my hint, how I would say it. I'm going to write it on the board because I have more room. Okay. When I'm saying it, I actually start on the left instead of counting the zeros first. I look at the commas. If the commas aren't there, I put them in. And I just pronounce it as I see it. This part is 100. If this was all we had and these zeros weren't there, it would be 100,000. But it's not 1,000 because we also have these. If it were just those, it would be 100 million. But it's not just those because we also have these, so it's actually 100 billion. 1,000, million, billion. I'm writing that because I don't want you to interpret my answer as the answer is 100,000 million billion. It's not. It's 100 billion, period. Okay. So we did the words. Now in your notes, write it in scientific notation. And, oh yeah, so this was 100, got that. And billion was billion, okay. And let's do it in standard scientific notation where you get the coefficient part to be between 1 and 10. So 1.0 times 10 to the something. And I want to know what the something is that goes there. I'm expecting that most of you have seen scientific notation before, but it might have been a while. So we're brushing up. And if this is tediously boring for you, bear with us. It's not tediously boring for everyone. All right? What I want you to say out loud is just the number that you would put here. I'll say this part. 1.0 times 10 to the what? 11. Oh, I don't even need to make you talk to your neighbor there. Yep. If you imagine starting here with the decimal point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Done. Okay. Usually more people get that wrong on the first try. Good for you. 100 billion. That is the number of stars in a typical galaxy like ours. That is a really big number. Most humans have, including myself, no intuitive sense of how big that is. I know it's a lot. I know if I saw it in a federal budget, it would be like a lot of dollars, but how many? What would it look like if I saw 100 billion of something? Have I ever seen 100 billion of something? Grains of sand on a beach? Mosquitoes in a swarm? To get a more intuitive, visceral sense of how big a number that is, let's relate it instead of a number of things that you could see, which would just totally overwhelm your vision and you wouldn't be able to distinguish them as individuals. With grains of sand on a beach, you can't possibly comprehend how many individual grains there are. They just kind of all blend together. But if we relate it to time, which is something that humans have a human experience range from very short, a split second, when you slip on something and fall, or when you blink your eyes. We're familiar with things that take a small fraction of a second, but we're also familiar with things that take many seconds, hours, days, weeks, months, and years. And if we study history, centuries, even millennia, we can have a sense of that. So let's relate 100 billion to time by using the smallest unit of time that is in everyday use, seconds. How long is 100 billion seconds? And I phrased it as how long would it take you to count to 100 billion if you counted one number per second? And yes, I know the answer is 100 billion seconds, but I want to know how long that is in relation to human experience. So in more practical, larger units, do you think it would be naturally measured in days, weeks, months, or years? A for days, B for weeks, C for months, D for years. Let's take a quick vote. Three, two, one, vote. Okay, I'm seeing at least a couple of each answer, but I'm seeing more years than others, and that's correct. It would be some number of years. Yes, it would also be some number of days and weeks and months, but let's go right to years, because it's more than a year. This is a natural opportunity to practice one of the math skills, unit conversions. Raise your hand if you've done unit conversions in a previous class. I'm seeing almost every hand. Let me take a quick vote. If I asked you to do this problem on your own right now and turn it in for a test grade, which I'm not, how would you feel about that? A, super easy. B, I could probably use a little refresher, but not too bad. C, ugh. I may have done this before, but I've forgotten. I would not feel good about that. Please do not do that. D, holy crap, I would rather die. Where is the drop form so I can get out of this class? So A, super easy. D, holy crap, I'd rather die than do this problem on my own without help right now. 3, 2, 1, vote. Okay, I am seeing A's through D's, my friends. We have a mix, and all of you belong here. So I need to ask you to be patient with your neighbor, because they may not have voted like you just voted. And the fact that I saw some D's and some C's and quite a few B's means that it's worth our time as a class to go through this example problem right now. And for the significant number of you that voted A, please have patience with us. Not everyone is as comfortable with this as you. But I'll try to go through it sort of quickly. when I do a unit conversion problem, I like to start with the quantity I'm given in the units that are given, and then multiply by conversion factors. If you learned a different way of doing unit conversion problems that you prefer, great, do it your way. I'm just showing a way for those of you who voted C and D that kind of don't know where to start. So I want to get from seconds to years. The way I like to multiply by conversion factors, personally, is to put them as a fraction and put parentheses around them. And I want to get rid of the units seconds. So I'm going to put that in the denominator. And then I want to get into the units I want to get into, which is years. Now, if you happen to know how many seconds are in a year, or have that information available to you, like on the equation sheet for an exam, fine. But if, in this case, you don't carry that number around, I would expect nobody to carry that around, then we can do it in smaller steps. Instead of going right from seconds to years, we can go from seconds to minutes, and then minutes to hours, and so on, all the way up to years. And I'm putting seconds on the bottom so that when I multiply later, that is going to cancel. And I'll be left with the units I want to get into. OK, and then I lastly put in numbers in front of those units that make the top equivalent to the bottom, and that is the redeeming quality of a conversion factor, which is, as a fraction, it's mathematically equivalent to 1. So multiplying by it doesn't change the amount of stuff you have, it just changes the units that it's in. So it changes the way it looks. So what number do I put in front of minutes? 1. I'll do 1. I mean, I guess I could put any number in front of minutes as long as I put the correspondingly proportionally correct number for seconds. But if I put 1 minute, then I have to put 60 seconds because 1 minute equals 60 seconds. All right, well, I'm going to just keep going and string all these together to get all the way from seconds to years. I know how many minutes are in an hour. 1 hour has 60 minutes. OK. Then I want to get from hours to days. What do I put on the top of this fraction? Hours or days? Days. Because I want hours on the bottom so that it will cancel with the hours up here when I multiply later. OK, 1 day is 24 hours. And my last one, I'm going to go from days to years. So what do I put on the top of the fraction to go from days to years? Days or years? Years, yep. So that days can go down here. The reason I'm asking you guys to fill in these is so that gives me a sense of how easy or hard people are finding this. If I get a quick answer in a loud volume that tells me it's easy, go faster. But if I hear a lot of hesitation that tells me it's hard, slow down. So I'm going to let you guys throttle how fast we go through this. OK, so what do I put in front of the year? And then in front of days, we'll do 365, 365.25 if you want some false precision on this calculation here. All right, then I cancel the units that, since these were all multiplication symbols in between there, that's what we do with the conversion factor as we multiply, that appear on the numerator and the denominator. Hours, hours, days, days, great. So now I'm left with just units of years. And that's what we wanted to do, is get from units of seconds to years. I didn't cancel all the numbers, and so those remain. Nothing in the top except for times 1 will get multiplied by our 10 to the 11, and times 1 will not change it, so I'm just going to leave it, leave off the times 1s. Then the denominator has some more junk in it, 60 times 24 times 365. OK, usually by now, someone will have plugged this into the calculator and have an answer for us. Oh, and our units, by the way, here are years. Anybody got it? Go ahead and say it out loud if you got it. 31, and we don't need, since I wasn't very precise with the number of days, I'm not going to use any more decimal places there. It's not million. Thousand, yeah, 3,130 or 3,100. And we'll round 3,200 years, 3 millennia. If you counted, now let's step back to what we were counting in the first place here, the number of stars in our galaxy. 1 per second, without stopping to sleep or die, you would be counting for 3,000 years. Hundreds of billions, heck, even billions. A billion would take you 31 years and some change. You don't live a billion seconds until you're in your 30s. Billions are big numbers. And that's just the number of stars in our one galaxy. We estimate, because there's too many for us to count them all separately so far, and we can't see them all clearly, that there are hundreds of billions of individual galaxies out there. So the total number, and that's just in the observable universe. Beyond that, who knows? So the total number of stars in all the galaxies in the observable universe is hundreds of billions times hundreds of billions. 10 to the 22. All right, big numbers, demonstrating unit conversions as we went. So we did this stepwise. We're like overtraining here, going crazy on unit conversions. But if you knew the conversion factor between seconds directly to years, you could do it in one step. And this is a good opportunity for me to draw your attention to the first couple pages of your workbook where I show you, DocCam, it's not going to work on overhead. If you turn to page 4, in your workbook, I actually tell you how many seconds are in a year, so you actually won't have to calculate that for yourself on homework or exam. And if you're curious, this is a really spread out version of all of these numbers and all the equations we're going to see later this semester, where it gives you the name of the equation and kind of write out what the different terms are. I give you the metric prefixes, so you won't have to memorize. Kilo is 10 to the third, mega is 10 to the sixth. Giga, by the way, that's the one that means billion. Astronomers love that one. I made a mistake in here. The negative sign, I accidentally left it out, so you can fix this right now. In your workbook, page 4, centi should be 10 to the negative 2, not positive 2. The brief version of this equation and numbers list is on the previous page, where you'll see exactly, character for character, what you'll be provided with on each of the exams you take in this class, including the number of seconds in a year. So that would have made this problem shorter, but with the same basic setup of starting with 10 to the 11 seconds, multiplying by a conversion factor, and getting the same answer, 3,200 years. Okay, so that, another very helpful thing while we're in the workbook, turn back to page 1. The students who have done this have really been glad that they did. We're going to take our break in a moment. I'm going to take a 3-minute break today. And after you've stretched your legs and done whatever you need to attend to your bodily needs, such as checking your messages, which I always need to do personally, I encourage you to fill this out. Use a pencil, because sometimes syllabi change or your schedule might change if you add or drop a class. But put the dates of all of your midterm exams. Look up your syllabi. You can look up the Astro syllabus on Canvas, and you can look up at your other syllabi. Use this for all your classes this semester so you have a snapshot view of when big deadlines are coming up, and you'll never be taken by surprise. Oh my God, I have 3 midterms in 1 week. You'll see that coming and can plan accordingly. So let's take our little break, 3 minutes, and then we'll resume with more example problems. Okay, let's come back together, folks. I'll turn off the music. I making you do unit conversions? I argue this is a practical skill. Let's get some examples. Even if you do it in your head, when might you do unit conversion? Let's get an example from each section of the class. We'll start with the left section here. Someone's got to help us out. Save us from the awkwardness. When could you do unit conversion? Distance. Convert from miles to feet, kilometers to miles. You visit another country, they say the city you want to go to is so many kilometers away, but you think in miles. How far is that? What's another? Money? Ooh, I had this picture my friend sent me last time they were at an airport. Well, actually, that was not last time. That was a long time ago. Yeah. They want to charge you so many euros for a lunch sandwich in Europe. Is that a good deal or not? How about another one from this section? What do you think? Time? Seconds to years like we did. As an example, might be others. How long will it take you to, well, rate problems are a related thing. If there are so many pages in a book and it's going to take you so many minutes to read each page, how long will it take you to read the whole book? That's a slight extension beyond unit conversion. That's more of a rate problem, but it's related. Did I see another hand over here? What's another? Cooking. Cups to ounces, tablespoons to cups, stuff like that. Yep. I already got a lot from these two sections. Anyone in this section have another one? Temperature. Fahrenheit to Celsius to Kelvin. Scientists, we love the Kelvins. Let's get one more. I think I saw another hand over here. Any section now. What's another? Weight. Kilograms to pounds. Those Europeans and everyone else in civilized countries, practically, it seems like, besides us, measures things in kilograms. Kilos. How many kilos am I? Is that good? Do I need to go on a diet? I don't know. Okay, so a valuable skill, I argue. Oh, I had some examples on here, but you guys already said all the ones that I... Oh, meters to feet. Okay, fine. Runners might be familiar with meters, the 1,600 meter dash and so on. But a lot of non-runners aren't. I'm just going to put up a cartoon for a moment of levity here amidst all this math. The phenomenon depicted here that these cartoon stars are talking about is real. It's called lookback time. In case anyone still needs to plug in your flipped attendance code for today, you can do that anytime during the class period. It doesn't have to be at the beginning, so you can still plug that in now if you want. Lookback time is this delay time. I mentioned last time it's one of the big ideas for the whole semester. I mean, the lag time is real. Sentient stars are not real. And the idea of sound traveling through space is false because sound cannot travel through a vacuum and space is a near perfect vacuum. But light can travel through a vacuum and readily does travel through space. So to more appropriately or accurately represent look back time with light and not sound, the stars perhaps should be saying by the time we see that youngster mouthing the words twinkle twinkle, that kid no longer exists. The lag times can be significant in astronomy. I've got a little 10-cent definition of look back time for you here. look back time always happens, even in this room. Whenever light is traveling, an analogous thing happens with sound. There's a lag, and sound doesn't travel as fast, so the lag is actually bigger. That's why there's a long delay between when you hear the clap of thunder and before that you see the bolt of lightning. There's a long delay with sound because sound is slow. Light is fast. So by the time you see that bolt of lightning, it actually happened in the past. How long in the past? Well, in the case of a few miles from you to a lightning bolt, it's a pretty small lag and you would never even worry about it. It's fractions, tiny fractions of a second. But the lag happens even with light, even in this room. So when you look here at me and I look out at you, I'm seeing you as you were in the past and vice versa. So when I look at a student in this class, what's your name? Jonan? Jonan's about, what do you say, 20 feet from me, guys? So the light that's reflecting off of Jonan from the source of light, the light bulbs in the ceiling, it's reflecting off of all of you, and that light that enters my eye is how I see you. The lag time is, with light, a billionth of a second for each foot. So I'm seeing Jonan as he was about 20 billionths of a second ago. I don't even know if he's still there anymore. Probably couldn't get very far in 20 billionths of a second, so I don't really worry about it. But the lag time is minuscule in everyday life, so we never worry about it, but it still is there. And someone who's 40 feet from me, I see you as you were 40 billionths of a second ago, and so on. And even adding up to many miles in everyday experience, the lag is negligible. But in astronomy, the distances are vast, as with our scale model last time. So when we go out to something like the moon, the farther away we look in distance, the longer back we see in time because the lag is proportional to the distance. So when we sent astronauts to the moon in 1969, that was when humans first stepped foot on the moon. We were communicating with them even before they got there, sending signals back and forth using radio wavelengths of light. And there was a lag. We see the moon, and therefore we got the signals from the astronauts when they were on the moon as they were 1 second in the past. So when people watch the TV broadcast at home of the Apollo astronauts communicating with ground control in Houston, there was this weird, kind of annoying, surreal lag when Neil Armstrong said his famous "one small step for man, a giant leap for mankind," and then the conversation, continued from there. Like, "Hey, Neil," I don't remember what they said. "How's it going, man? How does it feel to be on the moon?" And there was this delay before his answer came back. It was the round trip travel time of the signal, 1 second there, then he got the information, heard the question, formulated his answer, uttered his answer, and then 1 second more lag back. So a 2 second delay, plus whatever time he had to think about it. And who knows, maybe he was oxygen deprived and had to think a little extra long, but the delay was unavoidable because of look back time. So we see the moon as it was 1 second in the past, we see the sun as it was 8 minutes in the past, and we see the stars that are visible to the naked eye on a clear night as they were years in the past. A few years at a minimum, because that's the lag time for light to travel from Proxima Centauri, 4.2 years. But most of the stars we see are much farther than that, and we're seeing them hundreds or even thousands of years ago. Some of them aren't even there anymore. I've been seeing Betelgeuse, the star Betelgeuse, in the news a lot lately, and because its brightness has been fluctuating, and so they're wondering, is it about to go supernova? If it is, if we're about to see the supernova, by the way, it actually happened years ago because Betelgeuse is that far away. So the supernova's already happened, and we're just waiting for that information to get to us. And we can't get it sooner. We can't. There's no way to find out if Betelgeuse went supernova 50 years ago, other than just waiting to see when that light gets to us. So it allows, look back time, us to study the history of the universe, but it also forces us to do so because there's no way around it. Question?
How long was look back time for the sun?
The sun, 8 minutes. Yeah, so if the sun exploded, we wouldn't know it for 8 minutes. We would just be in blissful ignorance, sunbathing and raising our crops and doing whatever with sunlight, and there'd be no way for us to know it sooner. No information can travel faster than the speed of light, not gravitational waves, not neutrinos, nothing. So the stars you can see with your unaided eye on a dark night from State College or out in the country, even better, some of them you're seeing them as they were thousands of years ago. If you know the right place in the sky to look, you can see the Andromeda Galaxy. It's the nearest big galaxy, and it's close enough and looks bright enough that you can see it without a telescope if you're in a pretty dark place. And you're seeing it as it was 2.5 million years ago. Those photons from Andromeda, whether you're using a telescope to look at them or your unaided eye, makes no difference, have been traveling across the vast distance between us and Andromeda for 2.5 million years just to land in your eye. So if you ever get a chance to look at Andromeda, don't blink, because you wouldn't want those photons to land on your eyelid. What a waste. Anyway, another fact about look-back time. If we're looking at Andromeda, we're seeing its light as it was, showing us how Andromeda was 2.5 million years ago. Some of the stars in that galaxy are long dead and gone, but we can't tell. I'm saying, just statistically speaking, it's likely that some of the stars are long dead and gone, but we can't say for sure, or certainly not which ones. Think about it in the reciprocal. If someone were in Andromeda, if there were intelligent aliens there, for example, and they had fancy telescopes and were looking back at us, what would they see? Sorry, that was the second question. What would they see? Reciprocity. They would see Earth as it looked 2.5 million years ago. They would have no way to know that we modern humans with our fancy technology spraying radio waves out into space with our transmitters were here. They wouldn't see back to the dinosaurs, because the dinosaurs died out 65 million years ago, but they certainly would see a much more primitive Earth, or at least the civilizations. Humans, modern humans, would not have arisen yet. Maybe some kind of more rudimentary rodents, maybe primates, not humans. And then the first question, when will we be able to see Andromeda as it looks now in 2020? And when would they be able to see us as we look in 2020 with our current TV shows and signals? What do you think? Any ideas?
2.5 million years ago? I mean, in the future.
Yes, 2.5 million years in the future, they'll see what we looked like in 2020 and vice versa. There's no way around it. We're forced to study the history of the universe. So this idea of look back time and seeing things in the past brings up a natural unit, a light year. It's next on our to-do list. Everyone's heard the unit light year before, but sometimes there are misconceptions about it, so I just want to tease those out, see how widespread those misconceptions are before I teach you what light year is. Prepare your cards. Three, two, one, vote. Okay. I'm seeing a few of each. The correct answer is distance, and only distance. C. I'm going to say this emphatically. A light year is a unit of distance. Now say it with me. A light year is a unit of distance. Now I'm serious. One more time. We got to burn it in there. A light year is a unit of distance, and only distance. I know it sounds like time. It's got the word year right in there. Makes you want to think it's time. It's not. It's a unit of distance. And more specifically, it's the distance that light travels in 1 year. Some of you may have already had an inkling about that. But how far is a light year in terms of other distance units that people besides astronomers use? Give us a chance to do another math practice. Well, we know it's the unit of distance, so we can at least correctly construct the question, how far is that in terms of other familiar units? And this gives us an example to do a rate problem. Get my workbook. Here we go. And you, gotta flip this. On page 4, the rate equation for constant speed. That's what we're going to be doing right now. There's the equation. You'll never have to memorize it. It'll be provided in abbreviated form on any equation list that you would have for an exam. And of course, you can always look at this equation list when you're doing homeworks. So here is the brief version of it on page 3, as you'll see it on every exam. Distance equals speed times time. So what we want to find is the distance term in that equation. And the other two terms, it turns out, and this better be the case, if you want to calculate an unknown from an equation, you better know what all the other things are. So you only have one unknown. The knowns are the time, 1 year, and the speed. And it's the speed of light. Also, a number given on that numbers and equations list. Okay, so I think we can go back to here. And on this. In this case, the equation is already set up in a convenient way. We don't even have to rearrange it first. Sometimes a rearranging will be in order, but not in this case. Distance equals speed times time already has distance off by itself on the left. Speed times time. All right, well, the distance in question is 1 light year. LY is the abbreviation I'll use for light year. That's why I put this up here. That's LY for light year. The speed in question is C is a common abbreviation used for the speed of light. And that's how you'll see it on the equation list. But the actual number for it, which you'll never have to memorize because it's on the equation list, is 3 times 10 to the 8 meters per second. And the time is 1 year. So you could put 1 year, do a unit conversion problem, because now you know how to do that. Perhaps you already knew. But I'm going to take a shortcut here and use my handy page 4 conversion and know that 1 year is 3 times 10 to the 7 seconds. About 30 million seconds. And both of these numbers are rounded, by the way. The speed of light is actually 2.998 times 10 to the 8 meters per second. And the number of seconds in a year is actually 3.14 times 10 to the 7 seconds. I'm rounding. I encourage you to do the same. As a practical matter, virtually all of the homework questions and all, no qualifier virtually, of the exam questions will be multiple choice in this class. And so the answer options will not be close enough together that rounding would steer you astray. So round brazenly. Okay, so 1 light year equals, when we put these together, multiplying, since this unit of meters over seconds has seconds in the denominator, that's going to cancel with our seconds not in the denominator, and we're going to get an answer in meters. And it turns out to be 9, approximately, let's round again, the overall number. Well, without looking at the answer, at least we can do this part without a calculator. 3 times 3 is 9. And what, now I'm going to ask you guys to do this part, do I get when I combine these two powers of 10? 10 to the 8 times 10 to the 7. 15. We could do a unit conversion and put that into kilometers. And the workbook, I keep, oh, it's under my arm, gives, if you look on page 4, I'm not going to turn on the document camera again, but you've got your workbook in front of you. It says 9.5 times 10 to the 12 kilometers. And indeed, from kilometers to meters is a factor of 1,000 or 3 powers of 10. And the 9, we rounded the 3 here and the 3 here, so it's actually not exactly 9. It's a little more than 9. It turns out to be 9, closer to 9.5. And that's what you have in our workbook, and that's where that comes from. Beautiful. Okay. Let's get 2 everyday life examples of when you might care about the distance equals speed times time equation and apply it to something practical. Let's get someone from the front half of the room. What do you think? Traveling to a nearby state. How far is it? How fast am I going to drive? How long will it take me to get there? Yep, then you'd want to rearrange the distance equals speed times time equation to get time by itself and take distance divided by speed. Same equation you start with. Back half of the room. Give me another example. Go ahead. If you're running a race. They measure your time on a stopwatch. You know how far you ran. You want to know how fast you're running? Want to convert it to miles per hour? Could you run next to a car and keep up? Anyway, yeah. Let's do our first minute paper before we're pinched at the end of class here, time-wise. Here's how this works. And raise your hand if you don't have one of the official minute papers from the back of your workbook. If you do have a workbook, and get out your minute paper now. If you don't have your workbook yet, get your workbook for next time. And I will have one of our LAs bring you a minute paper. Make sure you're using one of mine. As it says on my everyday handy info, if on a future day you forget your workbook, tisk tisk, we're going to be doing a minute paper every day. And I do not want you to use notebook paper. Do not ever use notebook paper. I have a thing about it. I don't want to kill more trees and other reasons. I will bring spare minute papers every day if you need them. And if you end up needing to use one of my spares, you'll get like a tiny deduction of credit. But if you use notebook paper, you'll get a big deduction of credit. So bring your workbook to get full credit. Use my spare to get almost full credit. And use notebook paper if you really want to tick me off. But those will be sitting down here next to the spare voting cards on every future class period. Just grab one before class so we don't have to waste this time talking about it and having my poor LAs run up and down the stairs. Usually minute papers, it's not like writing a whole essay or anything to fill up the paper. Sometimes it'll be as short as a one-word answer. But today I need just a few words. I'm asking 4 questions, number these. This will allow me to address you respectfully. If I draw your name from the hat, or if I see you before class and want to say hi. And for number 3, this is your opportunity to opt in or out of the hat. If you don't know what I'm talking about with the hat, watch the recorded lecture from last time. It won't be recorded every day, but it was recorded yesterday and today to help people that add over the weekend to catch up. If you're not sure about the hat, you can put not sure, or you can just pick one, flip a coin for yes or no if you don't care, and you can always change your mind later, as detailed in the syllabus. You can send me an email later if you want to switch either from yes to no or vice versa. And my pronouns are she, her, and hers, by the way. Okay, while you're finishing those up, make sure your name, as it appears on my roster, and your user ID, that is your email ID, are at the top so that I can properly give you your participation credit for today. Hand your paper to the nearest aisle where the LAs will make a trip up and down the other side to collect those. While we move on to our last topic of today, constellations. So, this is a constellation that we mentioned last time. Some of you recognized it and even shouted it out when I asked. That's how it looks in the sky. And this is a cartoony way of doing an imaginary connect the dots to show a shape. And a more fanciful illustration is there. Before they had TV and modern entertainment, books and stuff, they used the sky for entertainment. And they made up stories about it, mythological figures and creatures and great battles and such. So Orion's a hunter, or a warrior. So that's what constellations mean historically, and how you have to use your imagination to connect the dots. It's arbitrary the way that the dots are connected, by the way, that Betelgeuse is considered a member of this constellation rather than whatever the constellation is right next to it. It's totally arbitrary. Where do you draw the boundaries? Arbitrary. But let's get deeper into the science part of it. The stories are fun and amusing. What about the science? Anybody like more time? Okay. By the way, you never have to write down the questions in your notes. The PDFs of all the questions are posted on Canvas in the recommended reading folder. And they're even posted before class as a draft and updated after class to reflect what we actually got through. So use this time for thinking, not writing. Well, I only have 2 minutes left, so I'm going to go ahead and give you a chance to vote. Prepare your cards. 3, 2, 1, vote. Okay, I'm seeing mostly C's and E's with a smattering of others. Here's another constellation, or actually a smaller part of a constellation called an asterism that many people are familiar with, the Big Dipper, with the distances to the various stars labeled in the units that you're now familiar with, light years. They vary by almost, not quite, a factor of 2. So some of those stars are almost twice as far as others in that constellation. And so it's not that they're the same distance from Earth, and therefore we can eliminate, since let's go back to Orion. Here's what it would look like if you could see it from the side. Since they're not the same distance from Earth, they're not close enough to be gravitationally bound together, and there's no evidence that they formed together because stars that do form together, which can happen, are close together. And stars in a constellation are not close together, so the correct answer is absolutely nothing. And so the second part, how I would summarize the information that this question gives, is that they're nowhere near each other in space. It's just a chance alignment from our perspective of stars that appear to be near one another, but they have nothing to do with one another. Okay, that's it. That's all we're going to say about constellations this semester. And astrology, from now on, we're going to stick to the astronomy, and I look forward to seeing you on Tuesday. Thanks, everybody.